Hi, let's talk a little bit about QoS, quality of service. Quality of service, QoS, what is it? It's a way to prioritize certain types of traffic over others, such as video traffic, voice traffic, or some kind of time-sensitive financial transaction. So a way that we want to kind of, when you're in line at the store or something and you want to give, you want to give somebody that has 2 items maybe priority over somebody that has 50 items in their basket, or somebody that's in a real hurry or something like that. Some way to prioritize these things. Also showing down here like a carpool lane or something, giving priority to somebody that is carpooling over those that are not. Okay, so example, packets are buffered. We see this example over here on the left that we have packets being buffered into 3 priority queues. Maybe a high priority queue for voice traffic, a medium priority queue for maybe some time-sensitive financial transactions, and then everything else goes into the low priority queue. So why and when do we use quality of service? Well, we use it because of congestion. And by the way, QoS is only enabled during times of congestion. So we don't need to be, the devices, the routers, multi-layer switches, don't need to be performing QoS unless there is congestion. So when there's no congestion, then we don't need to worry about it. Okay, so what is congestion? Congestion happens when there's multiple communication links being aggregated, meaning we got multiple links coming in and we have all trying to use the same link going out. And maybe that link is slower, or maybe there's fewer links or whatever it might be, but we have more traffic coming in than we can handle going out. So basically when there's more ingress traffic coming in than the egress, the outbound links can handle. So what do the devices do when they have more than they can handle, more coming in than they can handle going out? Okay, well, they put the packets in a hold, a queue in memory until the resources become available. Okay, so what does this do as far as the packets? Well, obviously it causes delay. Okay, putting somebody on hold while you're taking care of somebody else, they're going to be delayed. So new packets can't be transmitted until the previous packets have already been processed. It's like being in line at the store, right? You're in a queue, you're in a line. You have to wait your turn until the people ahead of you have been processed. Of course, that creates delay. If there's too many packets coming in and the queue fills up, then those packets are going to be dropped. So one QoS technique is that we classify the data into different queues, like we can see here. And again, QoS is only implemented when there's during times of congestion. Okay, so some of the things we have to think about here are bandwidth, congestion, delay, and something called jitter. So an interface is going to experience congestion when it has more traffic than it can handle. And we can kind of see some examples of this here. We have multiple links here. Let's say we have a lot of traffic coming in on these links, but going out a single link. This can cause some congestion, some delay, the problem can be worse when this outbound link is slower than, or doesn't have enough bandwidth to handle the capacity of the packets coming in on these inbound links. We can see this here with the speed mismatch, even with a single link. If we got a gigabit link here, the traffic coming inbound on a gigabit link, a lot of traffic, let's say, coming inbound on a gigabit link and having to go all outbound on the same 100 megabit link. Okay. And this is common in like LAN to WAN connections, your local area network to your wide area network connection. All right. So different types of delay, you can kind of take a look at these here, but delay or latency refers to the time it takes for a packet to travel from source to the destination. And there's multiple things that can cause this delay. There's both fixed delay and also variable delay. And jitter is a variation in the delay of received packets, meaning between one packet and another, the delay may vary. That's what we call jitter. And we'll take a look more of that in a moment. But here you can see the different types of delay, including queuing things like, the queuing delay, the amount of time it has to wait to be transmitted. And that's a variable because that depends on how congested the link is. But then we have fixed delays, things like serialization. The amount of time it actually takes for the NIC to actually process, physically process the bits and send it on to the wire. Okay, that's going to be a fixed amount, whether or not you have a lot or what, doesn't matter how many packets are coming in. That's going to always occur for every packet. Okay, so delay or latency, we say that refers to the time it takes for a packet to travel from the source to the destination. Okay, mentioned fixed delay, serialization, encoding and decoding, just what it takes for these bits to be serialized across the link, to actually be converted from the zeros and ones to the physical representation of those zeros and ones going across the wire. Okay, variable delays, talked about that, about congestion and how much time it spends in the network buffer waiting to be transmitted. So as a design rule, the total time it takes for a voice packet to cross a network should be less than 150 milliseconds. Millisecond being 1,000th of a second. We'll take a look at these rules more a little later. Okay, so without any kind of QoS, okay, the packets are going to be processed in the order that they're received. And we're going to talk more about that later. We actually call that FIFO, first in, first out. But so when congestion occurs, the network's will drop packets. If it has too many packets coming in than it can handle, it's going to drop those packets. Okay, so without any QoS mechanisms in place, we mentioned that packets are going to be processed in the order that they are received. When congestion occurs, network devices will drop packets. And actually in a healthy network, and we'll talk about this later in QoS mechanisms, packets will be deliberately dropped to avoid congestion. That sounds a little strange, doesn't it? But there's actually a reason for that. We'll talk about that in the later video on QoS mechanisms and why that happens. But I think it's in the later video and not in this video. I got to kind of think about that for a second. But anyway, it has to do with TCP streams being synchronized, and we'll talk about that either in this video or in a later video. Anyway, so what happens when there is packet drop? Well, if the end devices are using TCP, then the host, the end devices are going to take care of that. TCP will handle the retransmission of those packets. If the packet is using UDP as the transport protocol, then as far as UDP is concerned, it's not going to worry about any kind of retransmission. Perhaps the application layer might, but UDP won't. Typically, applications at UDP say that they can actually handle some packet loss. And this might be things with some perhaps some voice and video traffic. Not all video traffic, some voice video traffic that uses UDPs. It's, you know what, it's okay. We don't want to be retransmitting because it's going to, you know, receiving video or voice out or having to delay other traffic so you can retransmit a single voice packet that you might not even notice was dropped. Doesn't make sense. Okay, we'll talk more about that a little later. Delay, variation, or jitter. So delay, variation, or jitter is the difference in the delay times of consecutive packets. Okay, we want to have a nice, smooth arrival time. So we want one packet followed by another, and have the same delay in between those packets. So we want to minimize the variation in the latency. Okay, so as a design rule for voice traffic, that usually no more than 30 milliseconds of jitter. So when we see this in voice or in video, we see, like in video, we see a jerky motion, loss of video quality, even loss of video. The video and the voice can be actually get out of sync. And this is all because of excessive jitter. Okay, so an example here, a router receives a digital audio stream for voice over IP. Okay, so there's a playout buffer that tries to compensate for the jitter that is encountered. So you can see up top here the variation in the delay between the packets. The playout buffer it buffers that packet and then keeps the same delay in between those packets. Okay, so buffers the packets and then plays them out in a steady stream. Okay, if the jitter is too large, so if the incoming jitter is too large and packets are going to be received out of range out of this buffer, it can't buffer them well enough. So those certain packets will actually be discarded. And dropouts may be heard on the audio. It just depends. If the jitter is too large, then you're going to hear some dropouts, meaning you're going to hear that certain parts of words, perhaps even words, are not being transmitted. But for smaller losses, the digital signal processor, the DSCP, actually interpolates what it thinks the audio should be, and no problem is audible to the listener on the other end. But when the jitter exceeds what that DSP can handle, then audio problems are going to be heard. Some amount of jitter, some amount of loss is acceptable in voice, where you won't even notice a difference. But in properly designed networks with proper QoS, quality of service, and again, we only need that during times of congestion. When there's no congestion, this is not a problem. The packets are received with minimal delay, minimal jitter. But in a properly designed network, when there are times of congestion and we have proper QoS mechanisms in place, voice packet loss should be zero or very close to zero. We'll talk about that in QoS mechanisms, but there are QoS mechanisms that will give voice a very high priority over everything else to make sure that traffic is not dropped and receives high priority. Okay, there are some differences between video and voice. Voice packets, they don't consume a lot of resources. Okay, they're not very large. In general, voices, it's just audio. Okay, it can be handled very easily, and it's fairly steady traffic. Voice traffic requires less than 30 kilobits per second of bandwidth, and with no more than 1% packet loss. Now, video traffic is more demanding. Okay, the packets are bursty and greedy. Bursty meaning sends a lot of packets and then all at once, and then might be fewer for a while and then more at another time. kind of in bursts. Greedy means that it consumes a large portion of network resources. That video requires a lot of bits. So video is going to require a lot more resources. Requires at least 384 kilobits per second with no more than 0.1 to 1% packet loss. Okay, so some of the network traffic trends. So, you know, it used to be that everything was kind of web-based, text in the early days, in the 1990s and even the early 2000s. We had pictures, not as much video as we have today, you know, some pictures, and some voice. And we said voice traffic, right? Predictable bandwidth, known packet arrival times, data. Didn't have to be necessarily real, didn't have to be real time. Some delay is acceptable. But video traffic is increasingly becoming more and more important to business communications. We're using video a lot more. I know I use it a lot in my communications with, well, you're watching this on a video, right? And on the different groups I partake in, whether it's the California IPv6 Task Force or my work with Cisco or whatever, or my Cisco team, we're all over the world. And we use video to communicate with our meetings. According to Cisco's Visual Networking Index, video traffic represented 67% of all traffic in 2014. They said by 2019, which is actually just a month away, going to represent 80% of all traffic. That's not surprising at all. I'm sure it's not surprising to you either. Okay, so we said voice traffic, predictable and smooth, very sensitive to delay and dropped packets, okay, because we don't want this to happen, right? So we want a nice, smooth experience. It's very sensitive to any kind of delay. We don't want to be retransmitting voice packets if they're lost. Okay, because either that's going to cause delay, or we don't want, there's no reason to hear something after fact, right? After the fact. All right, I don't know if that made sense. But yeah, we need everything to happen in order and to be smooth. Okay, so we want it to receive a higher priority than other traffic. Okay, Cisco voice over IP and or IP phones and other voice over IP products use RTP, which is a real-time protocol, and those port numbers, as you can see there, and you can actually prioritize based on port numbers, whether it's a Cisco device or another device, doesn't matter, but you can prioritize based on port numbers. Voice can tolerate a certain amount of latency, jitter, and packet loss without any noticeable effects. So latency, no more than 150 milliseconds, jitter, no more than 30 milliseconds, packet loss should not exceed 1%. And that's because, the way that we speak and hear, that if there's a little bit of latency, a little bit of packet loss, you won't even notice. Okay, video, okay. Well, video, lost the mic there. Without any kind of QoS video, you're gonna see it's gonna be blurry, jagged, slow motion. I'm sure you've experienced this before. The audio portion may drop out or become unsynchronized with the video. Video, we mentioned before, it's birdy and greedy, drop sensitive, delay sensitive. So Skype, for example, when you Skype, it uses TCP for the connection and then UDP to transfer the data. Now, it might use TCP to transfer the data if UDP is being blocked by the firewall. Netflix uses TCP. And there's actually reasons why we want to send video that's not real time, like movies and things, over TCP. UDP, remember, just kind of sends everything. It does send everything. There's no kind of flow control or reliability mechanisms or any of that. Now, although video, we can get away with some packet loss in that, why do we use TCP, or why does the application use TCP? It does that because to actually do some congestion avoidance. UDP doesn't care about congestion. It doesn't even know congestion's occurring because it just sends it. TCP, with window sizes and acknowledgements and all that kind of good stuff that TCP includes, send window, congestion window, and all that kind of good stuff, both ends can determine whether there's any kind of congestion on the network. Okay, whether too many packets are being dropped, and what the application can do is can actually slow down the amount of data it's sending, so the other end can catch up, and hopefully there's a buffer there so you don't even notice while you're watching the video. And it might even lower the resolution or something, so the number of packets it has to send per frame can actually be less. Okay, so some of the one-way requirements: latency between 200 and 400 milliseconds, jitter between 30 and 50 milliseconds, and packet loss between 0.1 and 1%. Bandwidth about 384K. Okay, so we said so as far as data goes, most applications are going to use either TCP or UDP, okay? And as I just got done mentioning, TCP is a reliable protocol, actually performs any kind of error recovery. Make sure that any packets that are lost will be resent. So TCP is all about making sure that everything arrives there, okay, without any errors, without any corruption. That, you want to make sure when you're doing that online banking and you're transferring $100 between your two accounts, that it's not thinking it's $1,000. Okay. Now, some TCP applications like FTP can be greedy, meaning it consuming a large portion of the network capacity because you're uploading or downloading usually, a lot of information. So, although FTP, although it's important that you're sending the file, sending all this data, it's going to be relatively insensitive to any kind of drops or delays. I mean, you might have to wait a little longer. Even if you're downloading a web page, you might have to, depending upon the web page, maybe delay is usually not a factor, but it's definitely not a factor, or not, maybe an inconvenience, but it doesn't ruin the experience of downloading the file compared to watching a video, right? Okay, but we still need to consider the quality of the user experience. Okay, so, and even if it's not video or voice, the data may be really important. Does the data come from an interactive application? So, for instance, I think about even just being at an ATM machine or something, and you're there all by yourself maybe, and it's kind of dark out, and that you don't want the transactions that the ATM machine is taking to take too long. You want to get in and get out of there, just for your own safety. And is the data mission critical? So if it's a doctor in an operating room waiting for that data to show up on the screen to assist in the operation, and is looking at that data as the doctor is doing the operation. I'm not a doctor or anything. I'm just what I've read and what I've seen. But yeah, they don't want to have any kind of delay. That's mission critical information, isn't it? Okay. So some of the QoS mechanisms and algorithms. FIFO, first in, first out. So this is basically the absence of any quality of service. Okay, the packets enter the router, the order that they enter the router is the order they go out. Okay, we'll compare this with things like weighted fair queuing, that when packets come into the router, they're actually classified and prioritized based on a classification, and then sent out, higher class of traffic that is in the higher priority queues will get precedence. We'll talk more about weighted fair queuing in a moment, along with class-based weighted fair queuing. And there's also low latency queuing, which actually can be used to make sure that certain traffic like voice traffic doesn't get dropped, that they go to the head of the line all the time. But we'll be taking a look at more of these as through this video and in the next video. In the next video, which is QoS mechanisms, we'll look at FIFO, weighted fair queuing, class-based weighted fair queuing, and low latency queuing. Okay, but kind of a brief overview. So let's take a look at FIFO, first in, first out. Okay, this is where there's no concept of priority or queuing or QoS. The router, the device is going to make no quality of service decision or no decisions based on packet priority. Just doesn't care. What comes in first will go out first. Okay, there's basically one queue. Okay, this is like when we're standing in line at the grocery store. Okay, there's just you're in the queue along with everybody else. Okay, so when FIFO is used, any kind of time-sensitive traffic, and when congestion occurs, if it's at the back of the queue, and if the buffers and memory is getting filled up, that kind of traffic is eligible to be dropped. Okay, so when no other queuing strategies are configured, FIFO is the default on serial interfaces at E1, 2 megabits and below. We'll talk about what's on the higher end interfaces on serial links, which is weighted fair queuing by default. We'll talk about that in a moment. Okay, so FIFO is fine for large links that have little delay and minimal congestion. Okay, again, if there's no congestion or minimal congestion and enough bandwidth, then that's fine. You don't need any other kind of QoS mechanisms. Okay. Okay, so here's an example of FIFO. So first in, first out. So as those packets arrive, that's the order that they leave. Okay. Okay, involves buffering and forwarding packets in the order of arrival. Again, no concept of priority or classes of traffic. One queue for everybody, and everybody's treated equally. And when congestion occurs, that any kind of important or time slot, well, actually any traffic may be dropped, okay, just depending upon what came in last. Okay. All right. Weighted fair queuing. Okay, so I had mentioned I thought we were going to be talking about these in QoS mechanisms, but it looks like we're going to talk more about them right here. So let's get into weighted fair queuing. So weighted fair queuing is an automated method. And basically what it wants to do is provide some kind of fairness to everybody, okay, to the traffic, okay? It provides traffic priority management. Just does this automatically, dynamically sorts the traffic into conversations, okay? So it sees the conversations coming in, breaks up the stream of packets within each conversation, and make sure that everybody gets a fair amount of the bandwidth. Okay, so we can take a look here. Weighted fair queuing starts by sorting the traffic that arrives on an egress interface. that arrives on, let's see, that arrives on an egress interface into conversation flows. Should be actually ingress interface, shouldn't it? Okay, the router is going to determine what those flows are. So it's as it comes in. So we can see that it's getting some packets coming in here. So let's say this is just a kind of small packet, maybe a SSH connection. Or this might be an FTP transfer up here. This might be something in between. So let's say packets 1 and 3, and it sees these flows. So it sees a lot of packets with this flow and only one packet with this flow. And it's like being at the grocery store, right? You go to the checkout stand and you've got a basket full of groceries, and somebody else has one item. You say, why don't you go first? Okay, and that's basically what weighted fair queuing does. Okay, it's going to determine what the flows are, who has how much in every basket. The administrator cannot influence this. This is all done automatically. And how does it do it? It looks at, as far as these flows are concerned, it looks at them based on things like source and destination network address, the MAC addresses, the port numbers, and even we'll look at things like the quality of service, the ToS value in the IP packet or the Ethernet frame. We'll take a look at that a little later. Okay, there's also class-based weighted fair queuing. Okay, so what class-based weighted fair queuing does is allows you to actually define traffic classes based on certain criteria, protocols, access control lists, input interfaces. And then you can actually define, when a class has been defined according to its match criteria, you can assign it characteristics. So you can assign a certain amount of bandwidth, weight, maximum packet limit. Okay. So packets that match the criteria for a class constitute the traffic for that class. It's there's actually a first in, first out queue for each one of these classes. So as we're looking at this example up here, traffic is actually grouped into user-defined classes. Okay, so it sees this type of traffic coming in and says that's class 3 traffic. Okay, this packet here is a class 2 and this is a class 1. Okay, so it actually will prioritize it, giving priority of class. So notice here, although this is all in the buffer, and it actually put this class 1 type traffic to the head of the line, followed by class 2, followed by class 3. And this is all things that you can define with the different classes. So here's a little scenario here. This is from when I used to teach QoS in CCNP, but I want to show you just an example of this. This is a scenario. The administrator has decided that all high priority traffic should reside in the same flow, regardless of any other conditions that might take place, to put them in separate flows. So looking at, so here we've got 3 separate flows of traffic that come in, flow 1, flow 2, and flow 3. Okay, so you can see this is when they arrived. So what arrived first was the packets for the flow 3, followed by flow 2, then flow 1. Okay, so in class-based weighted fair queuing, okay, we can actually prioritize based on classes, and in this case here I'm doing it on something called IP precedence, which is a field in the IPv4 header, and there's also one similar field in the IPv6 header. And so what we're doing is we're based on certain criteria that has to do with the IP precedence value. We're in classless-based weighted fair queuing, the flow 2 is getting priority over the other flows. In weighted fair queuing, what might happen based on the time that the packet comes in and the size of the packet, that we can see there's actually a difference. This is done automatically, that this flow 2, that this packet here got priority, followed by then the smaller packet in flow 1, and then the packets from flow 3. Okay, so with class-based weighted fair queuing can be used to guarantee that flows received adequate bandwidth defined by the administrator. So that's really the difference. Weighted fair queuing is done automatically. Class-based weighted fair queuing allows the administrator to make that call. Okay, there's also low latency queuing. So what low latency queuing does, it has a strict priority queue right up here, okay? So, which allows delay sensitive data such as voice to be sent before all other queues. So it has this priority queue, and then it has the class-based weighted fair queues. Okay, so it's basically just puts a priority queue ahead of everybody else. So here in our buffer, we can see that, let me go through this here. We can see in our buffer, we have some voice traffic that jumps ahead to everybody else. So no matter how you configure your classes here, these user-defined queues or classes, the voice traffic is always going to get the highest priority. Yeah, and this is another way of looking at the same thing. There's a priority queue for the voice traffic, for delay-sensitive traffic. Okay, then everything else gets sorted into the user-defined classes, that class-based weighted fair queuing, where the administrator gets to decide on the different types of queues and what gets what priority, and then those follow after the priority queue. Okay, so that's a little QoS overview. We're going to talk a lot more about QoS in the next video, QoS mechanisms.